Okay, how is everybody today? Today we are going to talk about the multiplication rule. Okay, so remember last time we were working with probability and we were working with the addition rule, and the addition rule was when it said or. I want the probability of this or that. Now we're going to look at the multiplication rule, which means we're looking at a different type of probability. But before we get into that, we have another definition, okay, that goes strictly with the multiplication rule. And this says, two events are independent if the occurrence of the first event has no effect on the occurrence of the second event. Okay, so independent. Now, I know that we have used the word independent before, and yes, we are using it again. Sometimes, in different subjects, words get used too often. This independent, though, is possibly the most important word we will learn this whole entire class. Okay, we'll talk about that in a little bit. But what we notice here is when two events are independent, the occurrence of the first has no effect on the occurrence of the second, which means we're looking at events happening one after another. So I don't want this or that. I want this first thing to happen, and then another thing to happen, and then another thing to happen. So I want things happening in order or in succession. Okay, and that's when independence comes into play. Okay, so the idea is if you flip a coin, sorry, I have this little bug flying around my head. That's what happens when you're in the barn. If you flip a coin, bloop, flip it, I don't know, whatever, it lands tails. You pick it up, you flip it again, lands heads this time. Flip it again, heads again, whatever, okay? But every time you flip the coin, is each successive flip independent from the one before? And it is, that's why we use the coin, because it's supposed to be this fair coin, which means that every time you pick it up, you have an equal % chance of getting heads versus tails. Same thing with the dice. If you roll the dice once and you get a pair of sixes, are you more likely to get a pair of sixes the next time? Or less likely? Or is it just a crapshoot and you're gonna get what you get, right? So rolling the dice or flipping the coin, these would both be independent events. Okay, independent events. Now, one thing that would not be independent is dealing out cards. Okay, so we're not going to draw one card from the deck. We're going to play a game of cards. And as you deal out cards, what happens is the first card dealt comes from a full deck. There's a card sitting over there. And then you turn to the next person and you want to deal them a card. But has the deck fundamentally changed? Okay, it has, because there's already a card sitting over there. So now the deck only has 51 cards in it, so the deck has definitely changed, but it even goes further than that. What if you, as the second person, really wanted the 3 of diamonds, it's your favorite card, but I just dealt the 3 of diamonds over there? Is there any way you can get the 3 of diamonds now? There isn't, because the deck has changed. So flipping the coin and rolling the die, these guys are independent. But dealing cards is one of the best examples of being dependent. So dealing cards is dependent. Now, when things are dependent, when our events are dependent, it doesn't mean we can't do the problem. It just means we have to think about it quite a bit more. So we'll deal with that in a little while. Let's talk about independent a bit more. So honestly, as I said, This is possibly the most important thing you will learn in this whole entire class. If you learn nothing else, independence is the key. Independence in probability. That idea of being able to flip the coin and every time you pick it up, it's independent from any other flip is what we're looking for. And if we want an example of this, I have a great example. So hopefully most of you remember, but some of you are probably kind of young, but in 2011, they had the huge earthquake in Japan. And it wasn't the earthquake that was such a big problem, but the earthquake created a tsunami. And the tsunami took out the nuclear power plant that was on the coast of Japan. Okay, it was so bad that we were afraid we were going to get fallout over here. It was a huge, huge big deal. So what happened was the whole power plant wasn't taken out. What was taken out was the cooling systems. And I mean, I'm not a nuclear physicist or anything, but apparently you need to keep that nuclear crap cold. Okay, so the engineers, these Japanese engineers, for weeks after this accident, they got up and said in press conferences and in interviews, they said, this never should have happened. There was a 99% chance that the cooling systems would not fail. And they went on to say that they had the main cooling system and then 3 backups. So there were 4 cooling systems altogether. And the idea is if one of them failed, then the next one would start up. That one fails, the next one, and then finally the 4th one. Okay, so they got up and they said, those cooling systems, they should have worked. There was a 99% chance that they would keep the nuclear power plant, stuff cool. And this went on for weeks. And they investigated it and everything. And these cooling systems, like I said, there were 4 of them. They weren't attached to the nuclear power plant using the same pipes, or they didn't have the same electricity. So if the power went out on one of them, the other one still had power. So why did these 4 cooling systems, where did this 99% chance that we wouldn't have this failure come from? So after weeks, it was a high school statistics teacher from, I think, Wisconsin. And he called up his local newspaper or called up the local news, and he said, yeah, you know what? The reason why the cooling system failed was because they weren't independent of each other. And all of a sudden people were like, well, what are you talking about? Independent? Independent of what? What do you mean? So again, they went and they looked at it, and there were 4 separate cooling systems. They were all on their own cement pad. So they were not attached to each other at all. Pipes, not attached. Electricity, not attached. But here's the dealio. They were sitting 1, 2, 3, 4, right next to each other on the ocean side of the power plant. So a big wave comes, and if it's going to take out one, it's going to take out them all. And that's exactly what happened. So they were not independent of each other. If the first one fails, there's a better chance that the second one will fail because they're sitting right next to each other. Okay? So what happened was, here we're talking nuclear physicists, and they possibly, destroyed their part of the world with nuclear fallout, okay, because of this one word, because they didn't take into the account what independence really means. So the probability that the 4 cooling systems were going to work, if they were independent, was 99%. The probability or the chance that they did work because they were dependent ended up being 0. That's how important that word is. It can change probabilities from 99% to 0, okay? So we want to be very clear that everything that we do, that we're looking for this independence. And we'll talk about it a number of times, but the funny thing about independence is it's one of those things where we'll talk about it, and then eventually we just kind of assume of course they're independent, and we just move on, and we forget how important it was. So I'll try to kind of always come back and say, hey, remember independence? Hey, remember independence? Because it really is super important. Okay. So let's talk about independence events. So, and then we'll look at the multiplication rule here. We'll do the dependent events, we'll do that later. Don't worry about that right now. So the multiplication rule. This says, if A and B are independent, then the probability of finding A and B is equal to the probability of A times the probability of B. Okay. So if we're doing a problem that is things happening in succession and we want the probability of A and then B, now I like to use proper grammar, so I actually put a little and then in there. If you can say, I want to do this and then I want to do that, that's what tells you you're doing things in order. If they're independent, it's just a simple multiplication problem. Okay. Right? So with that being said, let's start with one of our simple independent ones here. Let's say that you are going to flip a coin. Let's go 4 times. And we want the probability that you get heads, heads, tails, heads. Okay. Now, right off the bat in this first example, notice the word and is not there. I wrote, find the probability of getting heads, heads, tails, heads. So you actually have to think about it yourself, and you have to say, I flip the coin, and then I flip the coin again, and then I flip the coin again. And every time you say and then, that's that multiplication going on. And because we decided that the coin is independent, basically that means we can go the probability of heads times the probability of heads times the probability of tails times the probability of heads. Ran myself out of the room there. Okay. Now, the thing about all these probabilities is they're actually the same, aren't they? So it's 1/2 times 1/2 times 1/2 times 1/2. Okay, which you could either put into your calculator like that, 1/2 times 1/2, or you could go 0.5 and could we raise it to the 4th power? Okay, so we go 0.5 to the 4th power. So 0.5 and use your caret to the 4th power. So I got 0.0625. And remember, the way you do that is you go 0.5 and then the caret to the 4th. Okay, use your caret key. Okay, so look at this. There's a 50% chance that you flip the coin one time and that you get a heads. Okay, but if you want 4 things to happen in order, look at what happens to that probability. In the end, to get a heads, heads, tails, heads, there's actually only a 6.25% chance that that's going to happen. So what happens is, as you want things to happen one after the other, that gets harder and harder and harder. So what we should see is we should see these probabilities drop quite low, which is what happened here. 1 time is 50%. If you want it to happen 4 times, 6.25%. All right? Okay. So in this class, primarily, we're going to be looking at empirical probability examples, right? Statistics examples. This guy would be a classical. We didn't get the coin out, we just thought about it. So classical, but let's look at some empirical examples. So last time when we were doing the addition rule, we used these tables, okay, for the addition rule. And we will use this again, don't worry, but I've got a different type of way that the empirical probability problems come to you. Sometimes someone will just give you a statement. So here is a statement. 70% of all lost remotes are found in the car. Okay, so let's be very clear. A lot of examples I make up, and that'll become much more clear as we go into this further and you see the different examples. A lot of them you can tell are totally made up. This one though is real, okay? This is an actual statistic. So apparently 7% of all lost remotes are found in the car. That's the only information that you're given. So what's the probability that someone loses their remote in the car? 7%. It's the only information we have, so that's what we go with. So that's what makes this the empirical type of probability. So in this case though, we want to do things in succession. So we need to select maybe 3 random lost remotes. Okay. All right, now this word right here is very important. You wouldn't think it was the most important part of the sentence, but it is. So we're going to select 3 random lost remotes. The random part is what gives us our independence, okay? So we're going to look for 3 lost remotes. But what I want you to think about in your own life, okay, where do you normally leave the remote control, okay? I'm probably thinking not many of you have actually left it in the car, but apparently it does happen. But, you know, normally when you lose the remote, the first thing you do is feel down into the couch cushions, right? Feeling around for it. But like in my case, I always take the remote with me, and whether I'm going to the bathroom or I'm going to the kitchen or I'm getting something to drink or whatever, I tend to put it on the kitchen table and then I go do whatever I want. So if I end up back at the television and I don't have the remote, I know that my pattern is to leave it on the kitchen table. So in that sense, if I was to lose the remote more than once, where do I go to look for it right away? The kitchen table, okay? Which means for me personally, losing the remote, that is not independent because I have a pattern. Other people will take it into the kitchen. People will even put it in the refrigerator as they take a snack out. They put the remote control in the refrigerator. If that's their pattern, it's something that they've probably done more than once, which means that if we're looking for the same lost remote, this is not independent. So we need to make this independent. So for independence, we might do something like this. Okay, let's say we run the lost remote control hotline. Okay, so we've run the lost remote control hotline. It's a little bit of a boring job, but you know, hey, it's nice. We're doing good deeds for people, okay? Charity work here. All right, so people call us up and they say, I've lost my remote control, okay? And we immediately say, did you check the couch? And if they haven't hung up on us by then, you know, or cussed us out or whatever, then we go through the process. Go check in the kitchen. Is it in the refrigerator? Is it in the bathroom? Is it on the kitchen table? Is it in your purse? Is it in the car? And we run through all of these places where it has a possibility of being with these people until we find their remote control. Okay, and then we wait for the next call, and then we run through the process again. So with that being said, the lost remote control hotline now gives us our independence. Okay, we're making the assumption that random people are calling in, I need to find my remote control, okay? Which means it's not the same family, it's not the same household, it's not the same person, okay? So someone calls in and they say, I've lost my remote control, and we go through the process with them fresh each time. So it gives us its independence, okay? Now, let's say we're having a boring night, okay? So we want to look at the next 3 random calls, okay? So we're looking at the next 3 random calls. I want to find the probability that all 3 of these, the next calls, all 3 are in the car. So we want to see what the probability is that the next 3 people that call, we find the remote controls in the car. Okay, now this is probably, you're thinking this is kind of slim chances, but let's see how this works. Now again, does it say and in the problem? Okay, it doesn't, does it? But we have to think about this. The first person is going to call in, and then the second person is going to call in, and then the third person. So there is that and then going on there. So what we need to do is find the probability the first one is in the car. So what's the chances that the first remote control is in the car? Well, the only number we have is 7%. So turn it into decimal, 0.07. Okay. We find that one, it's in the car, and then the next person calls in. The probability theirs is in the car is also 0.07. And then the third one would also be a 0.07. So we can either put that into our calculator or 0.07 to the third power. Let me see. 0.07 to the third power. Now, this, we get something that looks like this in our calculator. So what happens is probabilities are starting to get small, and so we start to go to scientific notation. Now, the thing to remember is that that exponent tells you how many decimal places there are to the left. So there are going to be 4 decimal places, which means there's going to be 3 zeros and then a 3, 4, 3. Okay. So the probability that all 3 remote controls are in the car is 0.000343. Now, do we round that to 0? We don't, because is there the possibility that it could happen? Is it very slim? It certainly is, isn't it? Okay, it's a very slim chance that it's going to happen, but it could happen. So we go out as many decimal places as we need to go, so lots of zeros, until we get to 3 significant digits. Okay, so 3 significant digits. So I never want to see that rounded to 0. Okay. All right. Okay, but we calculated it out. Okay. Now let's say that it's the next night, or it's the next night you're working at the Lost Remote Control hotline, and this time again, life's getting boring. So we're going to look at select the next 4 random calls, just to make it a little bit bigger here. Random calls. This time I want to find the probability that none of them are in the car. Okay. So this time we're looking for the first person that calls in, theirs is not in the car, and then the second person is not in the car, and so on. Now again, the random there is trying to give us our independence. These are independent people. It's not the same person. It's not Fred who keeps calling, I lost my remote. We go, damn it, Fred, go look in the car. And then he calls in and he lost, oh, damn it, Fred. So it's not Fred, okay? It's random people, random lost remotes. Okay, now, one at a time. What's the probability that that first remote is not in the car? If there was a 7% chance it is, then there's a 93% chance it isn't, right? So we're going to go 0.93, and then aren't we going to have 0.93 again and again and again? So could we go 0.93 to the 4th power? Right. So 0.93 caret 4, I got 0.748. All right, so this is looking at multiplication rule using kind of a different method, but still in that empirical probability sense. All right, so let's do another one, and I'm going to ask you some different questions here. Okay, this one is made up. 62% of farmers use John Deere equipment. Again, we're in my barn, so that's where the example comes from, and yes, there is John Deere equipment in this barn. Okay. So 62% of farmers use John Deere equipment. That's just some statement that somebody has studied and given us. So that's what we've got to work with. So now we are going to select 5 random farmers. Now again, the random is in there to give us that independence, all right? Now, just like a lot of people are about their cars, farmers are very kind of particular about their equipment. So if you're a John Deere family, you're a John Deere family. If you're a farmer and your grandpa was a farmer and your grandpa used John Deere, you most likely use John Deere. So we have to make sure that these are random farmers and like not all from the same family or from the same neighborhood, okay? They are just random farmers that we have picked out of a hat, okay? And that's what we're looking at here. And that means that it's independent. It gives us that independence. So select 5 random farmers. First, we want to find the probability that none use John Deere. So remember, this is a 62% chance that they do use John Deere. So I'm asking you for the compliment right off the bat, right? Okay. So if there's a 62% chance they do, then the leftover would be 38, right? So we're going to have 0.38. But how many times are we going to do that? How many farmers are we talking to? 5. So we're going to go 0.38 to the 5th power. And here I got 0.00792. Okay, so again, very small, less than 1%. Okay, 0.00792, and notice how I went all the way out. I didn't leave the zeros. Okay, all right. Next question. What's the probability, still selecting 5 random farmers, what's the probability that all of them use John Deere? So what's the probability that first one uses John Deere? That's going to be 0.62, right? Okay. And how many times do we want that to happen? 5, right? Okay, so 0.62 to the 5th. 0.62 to the 5th is 0.0916. Still a slim chance. So 5 John Deere users is still only 9.16% chance, okay? So both ways are kind of slim, all or none, okay? But that leads us to our next question, and this is the tricky one. The next one is to find the probability at least one uses John Deere. And here's the thing, whenever a problem has at least or at most or more than or less than, this problem is a challenging problem. So if you look at this problem and you see the at least, you should know that this problem is going to be more difficult than this one or this one. As soon as you see that at least, there's an extra layer of challenge in there. Okay, so at least one uses John Deere. Let's talk about what that means. Of the 5 farmers, at least one means 1 or 2 or 3 or 4 or 5. So at least one means that it could be any one of those options. It could be 1 of the 5 uses John Deere, 2 of the 5 use John Deere, 3 of the 5, 4 of the 5, all 5 of the 5. Okay, but that's a lot of work. It's a lot of work. So what we want to do instead is think about what the complement is. So if at least one is 1, 2, 3, 4, or 5, what's the only other option? Okay, what's the only other number of farmers that are using John Deere? And wouldn't it be 0 use John Deere? Right? if at least 1 means 1, 2, 3, 4, or 5, then the only other option is 0. Now, what's another way to say 0 use John Deere? None. So this could be said saying none. And do we already know the probability that none of these 5 use John Deere? We do, don't we? So this is going to be easier if we do this. We take, so the probability of at least 1 using John Deere is we use the complement, take 1, and subtract away what we don't want. We don't want these guys, right? That's the none, that's the complement. So if we take the 1 and we subtract away the 0.00792, okay, that should leave us with at least 1. So that'll be what, 99208. Okay. All right, so when you hear that at least or at most or that kind of thing, then you're looking at for the complement. So one more example here, and then actually I think then we'll be done. Let's say 83% of puzzles are missing pieces. So, just made it up, okay? So we are going to select 4 random puzzles. Okay, again, random to give us our independence. And this time I want to find the probability that at most 3 are missing pieces. All right, so as soon as we see the at most, again, like at least, we go, wait a minute, this is going to be more challenging. So we want to figure out what at most 3 means. At most 3 means that it can be anything up to and including 3. So could that mean 0, 1, 2, or 3? So at most 3 could be any one of those options. We don't know which one, so we'd have to calculate all of them. Real big old pain in the butt for us. Okay, real big pain in the butt. So instead, it might be easier to look at the complement. So remember, if we're talking about 4 random puzzles, at most 3 means 0, 1, 2, or 3. What's the only other option? Wouldn't it be all 4? So all 4 are missing pieces. Now, which one of these guys do you think is going to be easier to calculate? Do you want to calculate this, the probability of 0, the probability of 1, the probability of 2, the probability, do you want to do all of those? Because that's a whole bunch of little problems, right? Or would it be easier to just figure out what the complement is? Okay, so could we figure out the probability of all 4 missing pieces? So what's the probability the first one is missing a piece? Right, 0.83. So we'll go 0.83, and we want that to happen 4 times in a row. So we'll raise it to the 4th power. Let me use my calculator. Now remember what I said about using your calculator. Just because you're watching me here do it doesn't mean that you don't ever have to do it yourself. Make sure that you're practicing this as well, so you're seeing how to plug it into the calculator and what your calculator spits out. Okay, so plus you never know when I make a mistake and we might need to change it. So let me know if I've made a mistake. Okay, so I got 0.475. Okay, that look good to everybody? 0.475. That's the probability that all 4 are missing pieces. But is that what we wanted? Okay, this is not what we wanted, is it? This is the complement. So if we want to find the probability of at most 3, what are we going to do with this? We're going to go 1 minus 0.475, which should give us 0.525. So the probability that at most 3 puzzles are missing pieces is 52.5%. So you have to think about how the complement does affect you. So we've used a complement a number of times in these problems. And you have to kind of work it out and figure out what the complement looks like. Okie dokie. So that is the basis behind the multiplication rule when things are independent. Excuse me. When things are dependent, when events are dependent, like I said, it doesn't mean we can't do it. It just means we have to think about it a little bit more, and there's a little bit more to it. So that's called conditional probability, and that's what we will do next time. So this is just the multiplication rule. If you want to follow this right now with the conditional probability lecture, that's great because they kind of go like, again, one right after the other. But if you want to wait, totally your choice. All right, you guys? So have a little more fun calculating probabilities. Okay. Have a good day.